So we will not go into detail of LED structure, etc. Last day I have discussed a little bit about heterostructure LED, and there we have seen that there is some kind of confinement of carriers is achieved to improve the efficiency. Now there is two variations of these LED structures. They are namely surface emitting LED and edge emitting LED. Surface emitting LED is popular for fiber coupled devices. For fiber pictelled LED. So the structure is based on the heterostructure basic.
Sir, what is that after fiber?
What is?
Sir, what is written after fibers?
Fiber surface emitting LED and edge emitting LED. Surface emitting LED is popular for fiber pigtailed LED.
Okay.
Pigtail, it's a popular name. Actually, the fiber is grown, fused into the LED emitting point to improve the coupling efficiency. So it is like a tail of a pig. So that's why it is called pigtail.
Okay, sir.
So one is P plus gallium arsenide, which is the main source of the positive ions. Then P minus aluminium gallium arsenide. Then there is a narrow layer of gallium arsenide. It is also P minus minus. Then we have N plus heavily doped aluminium gallium arsenide. So this is the optical fiber. where the light is guided. Then, because gallium arsenide and aluminum gallium arsenide has refractive index close to 3, and whereas silica based optical fiber has refractive index close to 1.5, so there will be a mismatch. So the sites are basically matched with a index matching polymer. Generally it is epoxy resin. So this is a graded architecture where there is a major source of the positive ions are gallium arsenide, and then that is guided through aluminum gallium arsenide layer, which has a different band gap energy than the gallium arsenide. Then we have active layer. This is the active layer. Active layer is the having highest resistance due to the most lightly doped region. So therefore, if I apply a voltage between the electrodes, so then the major voltage drop, because these are conducting zone because of heavily doped N plus, P minus, etc. And P minus minus is the layer where the voltage drop will be maximum. So therefore field gradient, that is the electric field, will be maximum across along this thin layer. So there basically all those recombinations will take place. Hole will be supplied from this side, and electrons will be supplying from the N plus zone, and then recombination will be takes place here at gallium arsenide. One of the disadvantages of this surface emitting LED is that the light is generated mainly due to the recombination here. However, it has to go through this N plus layer and the subsequent buffer layer to be collected in the optical fiber. So therefore, that is one of the disadvantages. However, if we want to match the diameter of this optical fiber, which is in micrometer, typically single mode optical fiber diameter is 4 to 10 micrometer, and cladding is around 20-60 micron. So whereas this layer thickness would be a fraction of micrometer or 1 micrometer or 2 micrometer. So from this side, that is the edge side, connecting the optical fiber would be difficult. So to couple, the numerical aperture will not be matched. So that's why there has been some amount of buffer layer is etched out and filled with epoxy resin, and that epoxy resin filling up is done in a manner such that light is focused towards the optical fiber. So that way light is not only guided through this, the light which is also being diffused from this zone will also be coupled through the guided zone. That is because of the basic coupling mechanism. If two mediums, one is having the guided property, another is having non-guided property, they are very close to each other, then light tend to be coupled to the guided zone uh, for a certain space, for a certain length. And thereafter, of course, it tend to again come out. So therefore, this resin layer has to be narrowed down as within a very small distance, maybe a fraction of millimeter or at least 1 millimeter or so. So typically for LED, of course, this active layer is in micron, that is 2 micron, 3 micron, 10 micron, depending on the type of configuration. Whereas we shall see that for lasers, like laser diode, this active layer will be fraction of micron. Now, spectral purity mainly depends on the bandgap energy Eg and this can be mapped to a corresponding lambda g, that is bandgap wavelength. Lambda g and its temperature dependence. So with temperature, what will happen? The physical dimension of the band gap will change. So therefore the band gap energy will also change because of the expansion of the device. So this is the face to face of the conduction band and the valence band. And we know that corresponding to a wave vector, uh, so K, these are distributed in a discrete fashion. Now due to temperature, what will happen? That the dimension will change. So therefore this position will shift and maybe it can therefore allow certain amount of uncertainty around this wave vector K. So that is usually depends on the temperature and represented by a factor K subscript capital B into T. T is temperature in degree Kelvin. So correspondingly, if we plot the energy of the emitted photons and the intensity, i.e. So it will start from the band gap energy, and this will be sharp because below that band gap energy there won't be any recombination, but however above that there will be a distribution, and this distribution is determined by the factor Kb into T. So that's why the LED emission is though characterized by the band gap energy. However, the spectral purity is not that much because of the temperature dependence. If the device is cool, the spectral purity will be better. Then coupling to optical fiber is determined by the critical angle of the optical fiber. Which is known as which is given by the numerical aperture of the optical fiber. So this is the core and that is the cladding. So there will be an acceptance angle corresponding to the theta critical. So whereas there will be total internal reflection here. So this angle is given by the refractive index. So NR1 is the core refractive index. Which is slightly higher than the cladding refractive index. Equal to say sine inverse of AN, that is the numerical aperture. The coupling efficiency integration of 0 to theta A I theta sin theta d theta 0 to pi by 2 I theta sin theta d theta. Equal to sin square theta A. I theta is often I theta can be written as I0 cosine theta. Typical optical fibers have theta A around 10 to 15 degree. So coupling efficiency would be like 5%, 6%. So though there are advantages of pigtailed fiber, because free space coupling would be much more difficult, and also due to the movement of the optical fiber and the LED, so it need to be adjusted every time. So that's why if the fiber is fused into the emitting point of the LED, so it has a lot of advantages. Pigtailed fiber with LED has thus lot of advantages. Regarding coupling, efficiency, and packaging. Edge emitting LED is, on the other hand, light is emitted from the edge. So there is a metal electrode here on top.
Excuse me, sir. What is the heading that you have given? It's not visible. Can you scroll up?
Heading edge emitting LED.
Thank you, sir.
So then we have window for the electrode, and the other side is dielectric. Metal, dielectric, then we have this is indium gallium arsenide phosphide. So major source of positive ions are through a base of P plus INP layer. Then we have P plus indium gallium arsenide phosphide. Sorry. So this is indium gallium phosphide. The stoichiometric ratio can be varied by varying x, and thus the wavelength of the emission can be tuned a little bit. So this is the active layer, indium gallium phosphide, and then we have the N plus indium gallium arsenide phosphide, INGASP. Next we have N plus INP. Then the dielectric metal and dielectric layers are there as before. So this is the point from where the emission takes place. From the active layer. Edge emitting LEDs are efficient because this layer, active layer, is uh, sandwiched between INGASP layers. So therefore it provides both radiation confinement and the carrier confinement. Due to both efficiency of the device improves. Carrier is confined due to the differential band gap energy of INGSP and INGAP, indium gallium phosphide and indium gallium arsenide phosphide. The radiation is confined in the active layer, because of the refractive index of INGAP is slightly higher than the indium refractive index of indium gallium arsenide phosphide. So that way, that will act as a waveguide. So therefore, the radiation will be confined and it will come out of the front side. The back side is metal cased. However, the disadvantage is the dissimilar divergence of the beam divergence pattern of the emission. That is because of the device size. So this 120-degree is coming because the truncation of the size in the vertical direction is much more. So therefore, the beam will be diverged much more in the vertical direction, and in the horizontal direction it is larger. So truncation is therefore not that sharp. So therefore, that will be of lesser divergence.
So what is the X component in the active layer?
X component is the stoichiometric ratio. Like X could be, say, IN 0.5, then this is GA 0.5, or otherwise IN 0.3, GA 0.7P. So if I vary that, actually the uh, radiation pattern or the lambda G will vary.
Okay, sir. Thank you, sir.
So, okay, I can explain a little bit on that. So actually, if we take various materials, and the band gap wavelength, so if I take unary semiconductor like silicon, then silicon is band gap energy is 1.11 electron volt, and this is in micrometer. So correspondingly for silicon we have 1.15. However, this is indirect band gap semiconductor. Similarly, germanium also, if we take another popular detector device, that is 0.66, it can go to little bit more into infrared, 1.88 micrometer. This is also indirect band gap, so they are not used for source. Then there are binary semiconductors, ALP, like 2.45, it is in the visible zone. 0.52 is lambda g, but this is again indirect band gap. ALAS 2.16, 0.57 indirect band gap. ALSB 1.58, 0.75 indirect band gap. Then we have gallium phosphide, which is also a popular material, 2.26.55 indirect band gap. Most popular and was gallium arsenide initially because of the ease in deposition, 1.42, and also near infrared window 0.87 micrometer. This is direct band gap. GASB 0.73, 1.70 direct band gap. INP 1.35, 0.92 direct band gap. Indium arsenide 0.36, 3.5 direct band gap. Indium antimony 0.17, it goes to further into deep infrared, not deep, moderately deep infrared 7.3 micrometer, and direct band gap semiconductor. Now what we have used indium gallium arsenide phosphide. So how that concept comes can be explained by a diagram. This is EG. Lattice constant 5.4 angstrom. So corresponding to this, there would be wavelengths which I am putting in log scale. 1.52 and so 1.5 would be here. Maybe. So now INSP, if I put it is here, and indium arsenide is yes, there is some problem, I think.
Sir, the screen is not visible.